Okay, thank you. I actually wanted to start with another file first, just to kind of give you some feeling what this talk will be about without having any prejudice. I have a small trailer which I'll show you. And what you will see are green dots and red diamonds. Very spectacular. I will start the animation. It takes very short. It's up to you to kind of guess what's going on. By now, if you think I'm in the wrong session, because this is about flocking or swarm building, I can reassure you this is about evolutionary dynamics. What you see here and why I show this is the kind of general stuff of my first talk. When you lose me somewhere, when I'm getting too technical, with this you will have a handheld to continue to understand. What do you see here? You see two species, the green one and the red ones. They are very simple. Simple will be the key word in this talk. They have only two genes between 0 and 1. Which are the axes in this little animation. Now, what is the fitness of those populations? The green ones try to maximize the distance to the red ones. Okay, so their fitness is a kind of sampling of the distances of the red ones. How this will happen, you will see later. And the red ones try to minimize the distance to the green ones. So they sample the distance with the green ones and minimize it. In order to make it a nice, coherent story, actually they minimize the distance. Okay, they both maximize. One's maximize the distance towards the other ones maximize minus the distance. And then you get a behavior like this. Don't look on how fast or not it goes. There are pauses in between and sampling rates. Everything you will see happening with parameters between 0 and 1 in this talk live on torus. Okay, so you already saw it when I started the video. They just continue as if the border is not there because it's not there. It's a torus, a cylinder, and then folded together. So that just as a start to set some context on what's happening. And you saw that at the beginning, obviously the green and the red ones were distributed randomly over the entire torus or square, whatever you want. I'll go now to my PowerPoint. Okay, indeed, my title is somewhat provocative. I'm aware of it. It was the intention anyway. Where does coevolution lead to? And what I want to show is that with very simple models, you can actually show things. And even you can try to argue that despite that these models are simple, and they are really very, very simple, you can show to make it kind of admissible that this carries over to nature. They are, will I use this high technology? No, I won't. So there are three main concepts which kind of come together in this work. The first is coevolution. You saw it, two species co-evolving. Actually, they are co-evolving in a predator-prey-like way. Successful one is a failure for the other one. For one species to be short to the other one is good, but that's bad for the other one. Okay, a very simple predator-prey model. And if we look in the past, the main person who has started this coevolutionary work was Hillis with his host-parasite work in 90, then followed by other ones like Pollack and Potter de Jong, who did cooperative coevolution. At about the same time, around 93, 94, I developed my own coevolutionary genetic algorithm, which I call CGA, coevolutionary genetic algorithm. And I used it for a lot of optimization problems, okay? And then doing lots of other stuff, also symbiotic evolution with it, etc. This is pretty old work for some of you young guys. The second thing which comes around is the genotype-phenotype mappings, GPMs. Already for some time, the Human Genome Project, or a bit earlier, people were a bit disappointed. There are so few genes for such a complex individuals. So then it was realized that a lot of the complexity is in the networks interacting between the genes, and for example, the mapping between the genotype and phenotype. Related is the concept of evolvability. The only problem being that evolvability has a lot of different definitions. The one I'm using is the one of Wagner and Altenburg, where they kind of evolve also the parameters of the genotype-phenotype mapping. Again, you will find it too simple how I do it, but that we'll see later. The third concept is evolution to the edge of chaos, which is a concept which was kind of very hot in the late 80s, early 90s. People like Packard, Kaufman, Langton. We'll see during this talk how those three issues can come together. Now, this is the structure of my talk. Pretty standard structure. I first will introduce my coevolutionary genetic algorithm. Then I'll do the pursuer evader dynamics, and you've already had a preview on that. And then the kind of normal structure of a talk. So the coevolutionary genetic algorithm. You have predator-prey populations. You have two populations. The individuals are very simple, just two numbers, x and y. They are coordinates on the torus. They have a fitness. And these individuals are all ranked, just like in a Gentler-like algorithm, genetic algorithm, as people know from Whitley. The best ones are on top, and the worst ones are on at the bottom. This in order to ensure that you can do some rank-based selection. Then there is a bunch of code, which you don't have to read all, but that's the main cycle. Once you've initialized your two populations with random elements, you calculate their fitness, somehow averaging how far I am, what my average distance is, and then vice versa, how my negative distance is to the others. And then this fitness is continuously updated. Okay, so for this reason, all those individuals have little queue on which they get fitness feedback, and that's what happens in those 20 times. 20 times you select individuals in both populations. The higher ones have more chance to be selected than the lower ones. You do an encounter, which gives a payoff. In this case, just the distance between those two individuals. And you put this in their history and update their fitness. This history takes the fitness feedback it got over the last 20 encounters, and the fitness is just the average. So it's kind of running average over the last encounters. For one reason or another, I like the number of 20. And then in the second part, you see the reproduction in both populations. You select the parents, You mutate Chris over it, calculate the fitness, and then insert its child in its population. If its fitness is better than the lowest one, you put it at its place and it remains sorted. Okay? For this reason, I gave the video in the beginning. That's a much better intuitive understanding. Then the pursuer-evader dynamics. This I already told a bit as well. So they are both on a torus between 0 and 1, and they all maximize the distance or minus the distance, which means they minimize it. As I stuck to my standard coevolutionary algorithm, the reproduction rate per population is the same. So that's total nonsense in nature. That's obviously not true. We will see what the impact here is and even what you can learn from that. If you take hypotheses which are not true in nature, and perhaps that's what a lot of people don't want to hear really, but from time to time that can be useful as well. Actually here it means that as you have the same reproduction rate, that the smaller population, and in case the population size are not the same, will move faster. So if the evaders are smaller, they get the same reproduction rate, so they will be able to move faster. You can see this. I have a short video of this. So if you take the same video as before, but now the evaders are at 50 members in the population, and the pursuers are at 20. Those are the two first numbers in these quadruples you see. The zeros indicate that you will see something else later. If I start up, as the it were the pursuers which were faster, like this. Again, they form clusters, but now you see very quickly the red ones catch the green ones, and they kind of bounce into it, and then as the distance is on the torus, you need to calculate two distances and the minimum from them. You see that they go apart, kind of isolating and stabilizing the other ones, or in 4 parts, and so as long as they then go out, they kind of stabilize the other population. So that's the easy part. I hope I will get all of you with me for the rest. Now we're going to introduce
the second option from current slide at the top. Second from the right.
this one?
Yeah.
Okay. Good to tell people which understand PowerPoint technology. So from now on we had two kind of numbers describing the individual, an X and a Y, which was their place on the torus. We'll have 4. And actually what happens is we just apply those equations a couple of times, which is just the X. We add a small number, the alpha 0, 0.1 all of the time, multiplied by R1 xn. Once again, the R's are numbers on a torus between 0 and 1. So the genotype-phenotype mapping does nothing than kind of growing. It gets larger in small increments. And there are two parameters, the two ones which were 0 in the first movies I showed, and that's preg time and grow time. This kind of implements pregnancy. So once a new individual is born, the equation of x on x and I and y are applied at preg time numbers of times. And then it's put in the world. After birth, during each cycle, they can still continue a bit to grow. So then one step by one. So imagine that pregnancy is 50 and growth time is 20. That means that when it's born, immediately 50 times this kind of increment is applied. And then during each cycle, during which populations reproduce, 20 times this increment is being added. So I hope I get most of you still here. It's not that simple. It's not breaking rocket science. The main question is, where do R1 and R2 evolve to? And that's the point. We want to show how this genotype-phenotype mapping evolves and where it does to evolve, in which iterations. So hence we set up a lot of experiments. For each we did 100 runs of 20,000 cycles. And then there are some other things. I even didn't include mutation rate, which is pretty low because you have such a low number of genes. The notation, which you already saw in the movies, is first the number of populations in the evader population, then the pursuer population, and then you see the preg time and growth time, which initially is 0, which was the case in the movies I showed. Then at the end of each of those runs, how many were it? 100 I assume or something like that, we print out all the R1s and R2s for a population. So then you see to what those genotypes mappings have been evolving. Remember, you have one individual, whether it's in the evader or pursuer population, you have their coordinates, and then the R1s and R2s, which determine how much they are incremented during pregnancy and afterwards. When those last preg time and growth time are 0, obviously the R's don't play any role, and are distributed over this area. In the next section of experiments, we introduced a preg time of 80 and a growth time of 20. So now the genotype-phenotype mapping does do something. It does change the x and y coordinates. And you suddenly see a complete different picture, namely that they kind of cluster at the edges and at the corners. And that's for the evaders. What happens, I could tell you no because I'm a bit short of time. Because of the toroidal representation here, these are the places where you have access to maximum possibilities of behaviors. You can switch from here, not changing anything during the mapping, to there, doing a lot of differences, and then both variations. So what you do evolve to is to what I call ROMAs, which are regions of maximum adaptability. You can do further experiments like that. Conclusion from those experiments, which I won't go through now, is that as selection pressure increases, the pressure to go to those ROMAs for the parameters of your genotype-phenotype mapping is higher. And high selection pressure in this simple model is or when you are a large population size, because then you move slower, or when you use a lot of the genotype-phenotype mapping, so a lot of growing and a lot of pregnancy time. I'll go through this. So these are the ROMAs. So this gives, the central question is, where do those R's evolve to? They evolve to ROMAs, and their density shows somehow the strength of this attractor. So this was what I already told us. Selection pressure increases, larger pore size or larger rolls of GPM pressure to our ROMAs. Then the last discussion is, how realistic is such a simple model? And do the results carry over to the real worlds? The toroidal worlds ensure that you have a kind of ongoing evolution, but more important, there is no epistasis in the model itself, but due to the fact that you make small leaps and can have access to different behaviors, compensates for the lack of epistasis. And why we think it carries over is that we use the basic processes of evolution. Future research always kept. And then the conclusion, what we studied here is a very simple model of the dynamics of predator-prey coevolution. When genotype-phenotype mapping is under evolutionary control, as selection pressure increases, the GPM evolves to its ROMAs, and now ROMAs generalize the concept of evolution to the edge of chaos. Because the edge of chaos is nothing else than a kind of space where there's a lot of different types of behavior. And that's what you see here. Although there is no nonlinearity, there is no chaos, and you see again that they kind of go to the place where the maximum adaptivity is attainable. So, in other words, ROMAs are regions with high evolvability. That's in very short what I want to tell, and a bit more, but which I can't.
Thank you very much.
Okay.